Hello, welcome back. Today we're going to talk about how we can use the double integral to find area. You may recall last year from single variable calculus that one of the main purposes or uses of the integral is to find area. So today we're going to take a look at it using how we can use multiple integrals or a double integral to also find area. Yes, this is a little bit crazy what we're going to be doing today, but you'll see later on that there's going to be a reason that we're going to do this. So basically what it says is if R is a region defined between X is between A and B and Y is between two different Y values. So if I'm looking at a region down here, ready? Such as down here, and I have my X values going from A to some value B, and I have my Y values going from, let's say, what did they use? They use G, so I'm going to use different letters here, so I'll use C and I'll use D for my Y values. And that's what this says here. So we have our X values going between two different numbers and our Y values going between two different numbers. We can find the area by looking at this double integral. Now you notice right here we have this double integral where the change in X's, remember, is going to go from A to B, and the change in Y's go from, in this case, from G1 to G2, which we use down here, C and D. So you might recall from the earlier video that we did, we have this dy dx because that is the area of our rectangle, and we're going to talk about that again later on today. So if we have it in the form dy dx, we call this vertically simple. In other words, we're starting with our vertical rectangle from last year in mathematics, or in this case, everything has to be in terms of x. Or the first integral has to be in terms of x. We're dealing with f of x. Now likewise, we can even switch this around. Now it does change some things, and we're going to talk about that later on. We can do it dx dy. So now, in this case right here, the y's are going to go from c to d, just like here, but then our x's are a function. So this from like last year is our horizontal rectangle. You might remember that from another video from last year in single variable calculus. In this case, we have to be in terms of y, or f of y right there. So let's take a look at what this is really kind of saying right here. In a nutshell, let's imagine we have some function f of x. Now we know kind of here and it meets here. And we have this function right here. And what we want to do is we want to find the area underneath this. So I'll shade in the area. That didn't show up too well, so let's see. Wow. White does not work out too well on a white backdrop. There we go, so we choose gray. So we want to find the area of this rectangle. Well, if from last year, you might recall in BC, we can use a vertical rectangle. So I can draw a vertical rectangle down here. I'm going to make it a little bit thicker. And in my vertical rectangle, we can measure that by saying, taking the top function minus the bottom. And remember, this is dealing with the change in the y values. The bottom thickness, remember from last year, whoops, there we go, is going to be dx. The thickness down here will be dx. Remember, that's the smallest possible x value right there. So if the vertical rectangle gives me my change in y values, we can say my change in y values are the following. In this case right here, it's going to go from c to the function here. Remember, this function here is y equals f of x. So the smallest value we're looking at is going to be the bottom, or let's just do this for fun. The bottom, which let's say is c, my range is going to be from c to the function itself. Notice I did change c to the very bottom. In this case, c would be 0, just so we can have more of a generic case right there. In other words, we could say y goes from c to f of x, whatever c is. Now, next, let's imagine for last year, we also deal with the horizontal rectangle. So let's go ahead and draw our horizontal rectangle right there. Now, in the horizontal rectangle, we always measure right to left. Now, the horizontal rectangle represents the change in the x values. In other words, it gives us delta x. So, and this is going to go from A to B. Remember, because we're in terms of x, so my x values are going to go from A to B. Or we can say x is this from A to B right there. So the question is, well, how do we get the area? Well, look at this tiny little intersection. I'm going to blow this up here. Now remember, this is also dy right there, it's that thickness. If I were to blow this up, let's see here, blow this up. Alright, so we're looking at the intersection of our vertical rectangle and a horizontal rectangle. And we have this little tiny little rectangle in here. It's not a square, it's a rectangle. But a square is a type of rectangle, I guess. But what is the area of that one tiny little rectangle? So if we go over here, well, if I blow it up, that little tiny rectangle, it's going to have a bottom width of dx and a side height of dy. I can get that area by multiplying dy times dx. Now the reason I'm putting the dy first, and we're going to talk about this later on, is because our function's in terms of x. Right here, we'll talk about that later on today. So if I want to get the area, well, that's the area of one tiny little rectangle. But remember, we're going to have lots of them, right? So if I look at this little cross right here, all throughout this, I'm going to have all these tiny little intersections, infinitely many of them. So we're going to add them all up, and what adds them all up is, of course, our integral. But because I have two variables, I have to write a double integral, dy dx. And then I'm going to look at the domains. Well, remember from yesterday, we start with the inside first. This integral dy, and y goes from c to f of x. And then on my outside deals with dx's, and that goes from a to b. Now you might recall from yesterday in the notes, in our video, in our lesson, that the inside integral, the domain, has to be in terms of the outside integral. And that's another reason why we do dy. It's going to be y, if it's a function of x, dy goes first. And that would give us the area of our graph. So let's take a look here. Righty, let's take a look. Let's see how we can use this. So we want to write and solve. So we're going to take a look at what we did from last year. Okay? We want to write and solve an integral that calculates the area under the following curve from 1 to 4. So again, we're looking for the area. Here's 1 all the way to 4. So we're looking at this area underneath this graph. Last year, in calculus, in single variable calculus, we would just write a single rectangle. And because I'm in terms of x, we're going to draw a vertical rectangle. So if we look at that rectangle from last year, that rectangle of mathematics, this has a height of delta square root of x minus 0. So therefore, the area would be the integral, the square root of x, dx from 1 to 4. And we could calculate that integral by evaluating the integral. This becomes, what's that, u to the 1/2, so 2/3 x to the 3/2 from 1 to 4. And if we evaluate that, we would get 2/3. And let's see, plug in 4. 4 to the 3/2 is 8 minus 1. And so we would get whatever, 7 times 2 over 3, so 14/3 would be our area right there. Okay, please go into video number 2, and we're going to take a look at the same exact type of problem, but now we're going to solve it using multiple variable. And you might be asking, it's just as easy this way. I know, but we're crazy in multivariable, and I will see you then. Bye-bye.